Okay, good morning everybody. I hope everyone's having a wonderful day. So just as a quick reminder, remember that assignment 2 on paper is due by the end of today, but keep in mind the submission will be open without penalty until 8:30 in the morning tomorrow. So just don't push this 8:30 in the morning. This is like just me making sure that you have this available to you. You may use that additional time if you need to, but remember the true deadline is technically by the end of the day. So just be mindful that this time is being given to you just because I want to make sure things are accessible here when it comes to the assignment. And likewise, like I told you before, I'm not going to look at your assignment, nor is the grader going to look at it at 2:30 in the morning. So also another thing, I plan to put out assignment 3 sometime tomorrow. So I'm still working away on that. I hope that you'll find it rather interesting assignment. So anyways, is everybody excited about talking about trees today? So give me 2 thumbs up if we're excited about trees. I'm not talking about the trees outside, though. They're looking quite lovely. But I'm talking about these kind of trees, which I like to think of as trees like outside, but you flip them upside down. That's often how computer science people tend to draw these rooted trees, is they draw them like this with the roots at the top, and it's usually downwards like this. It's very common. So last day we were talking a lot about different tree terminology. Remember, the tree is you can think of it as a model of a hierarchical structure. Think of it like an organization of a company or like a file systems directories. So today I promised you I was going to talk about how you actually can represent the tree. Now I must stress that this is a rooted tree, which is much more general than a lot of the data structures we're going to see later based on trees. So a lot of ours are going to be specialized versions of these. So at first this is going to look a little daunting, but let me walk you through it. And I will show you it's not that much different than what we've already been playing around with. It's just, remember, just think of it like we're just generalizing the ideas from a linked list. So here's a picture of a tree here on the left. So for example, C is the root of this tree. So that node is the root. Now, what we're going to do is we're going to have a node that's going to be represented with 3 attributes in it. So instead of it being like where we have 2, where we have data and next, we're going to have 3 of them. Keep in mind, there's several ways you can modify this representation. I'll mention a few of those in a moment. So each one of the nodes will have a data attribute. It'll have a parent attribute and a children attribute or child. Well, so these are each going to represent the node's data, the parent, and the children of the given node. So keep in mind that the parent is going to be a pointer to another node. The data could be a pointer to some object. And the children is going to be a pointer to some iterable collection. Now, just before I get too technical about this, an iterable collection is any collection that you can access each successive member by simply indexing or getting the next element one after the other efficiently. So, for example, something like a list is an iterable collection. Things like a vector is an iterable collection. An array, technically speaking, is also an iterable collection. In fact, it's easy enough to think about our collections here as arrays. So, just to be clear, when some people use the word iterable collection, especially in some programming languages, they're explicitly saying that it has the ability to have an iterator. So, for example, a list has an iterator, vectors have iterators. You may have heard of this concept of an iterator during the lab. So the whole thing that I just need for this to work is just that I'm able to access each one of the child pointers for my children. I should be able to access each one of them in constant time, one after the other. So I don't need to access each instantaneous one in constant time, but I should be able to access them one after the other, like if I was using a for loop. Just like if I was trying to index into an array scanning from left to right. But very often, as we specialize our data structures, it'll be easy enough to imagine these collections just like they're an array. And if there's a constant number of them, you can even imagine them just as a bunch of variables. Just like I had a next attribute. So remember, this is just going to be a collection that's going to contain pointers to other nodes that are going to be the children. So let me draw, so this is going to represent that tree over there. So remember that this is a much more generalized structure than the things we're going to be seeing in upcoming lectures. But I must stress we're going to generalize further and further towards the end of the course. So notice I have a root here. So this is going to be represented as a node, like I said, with these three attributes. I have a data, which is going to be pointing to C, whatever C is. I'm just going to call it C. That will be a pointer to some object I'm calling C. It's going to have a parent attribute. Because it's the root node, it does not have a parent, so we know it's null, right? So that's one thing to notice about the root node. It's very special like that. Likewise, I have my child attribute, which points to a collection of elements. And I must stress that these elements are pointers to other nodes that are the children. So to make this easier to see all of these pointers, I made the child pointers red and I made the parent pointers blue. So in some representations, you don't need the blue pointers, but very frequently you'll see that the red pointers are present. So the reason why I keep this rather abstract at this stage is because I just want you to be aware of how we can represent the tree. So this could be an array, for example, which contains pointers. Just like if I had, you can almost imagine this, like if it was a linked list, if I had an array of length 1, where each one of them is just like the next pointer. But if I don't have any elements in my collection, I'll just presume that there is no collection that I'm pointing at that I can access. So, for example, notice that I have my leaf nodes, A, B, E, and D. Remember, a leaf has no children. So notice that each one of these, they do not have any collection of elements associated with them. So notice that each one will have a parent that we're going to presume that always there's a pointer to a parent. And I have my data attribute. So once you see this, it's actually really not that much more complicated. It's just that now we have this collection of pointers to these children. Is that clear, everybody? So it's really not that much different. It's just the fact that it looks a little more complex just because all now we're doing is we have a parent that lets us point back or go back up to the parent. So for example, if I'm at a given node like this, say if I'm at node B over there, notice that I can follow these parent nodes, the parent pointers to each node to get back up to the root. That's one useful thing about this representation. If I don't have the parents like this, I may have to use recursion to keep track of these things. But I want you to keep in mind that for every one of the nodes, I have a data, a parent, and I have the children. And the other point is that I can go through each one of these children, one after the other in constant time. Very often, when you have what we would call an iterable collection, you can almost imagine this using a for loop structure. Some people call it a for each loop, where you go through each one of the objects in that collection. So you can either specialize it further, like if you know it's an array, or if you're doing something with a iterator, it's nicely set up for you. So are there any questions about this representation? So I'm mostly bringing it up to you so that you have an awareness of what this is. So when you write up a class for your tree, you'll have a root attribute. So like this would be one of your instance variables. And that's actually the only one you'll have in that class. All the other ones will just be simply pointing from here, just like if you have the head of a linked list. If you want to keep track of how many elements you have in the collection, you can also have a counter variable too if you wanted. So this should draw direct parallels from the linked list. It's just a generalization like we talked about last day. So I like that somebody brought this up last day, and yeah, no, it's just like that. It's just now I have a few more pointers kicking around. So are we okay with this? I just wanted to make sure you could see how you'd represent this on a computer. So you just imagine this just as a node, just like you have with a linked list. Except now I just have more attributes. That's it. So you can do all sorts of things to these collections of nodes. So like you can insert children, remove, so on. You can imagine these just as some container of elements. Okay. So if we're okay with this, I'm going to proceed to now show you a very fascinating property that trees have. So you're going to find that we're going to be starting off with me just telling you a little bit more about trees, and then we're going to start seeing how we can design algorithms on trees, so that when we talk more about specific data structures that are built on trees, that you can actually see how we can adapt these ideas. So sometimes there's specific properties that the data structures have, kind of like what we've seen, for example, when we were playing around with things like stacks and queues. There are specific properties that the data structure had that we can use to take advantage of. Likewise, we can do the same thing with our trees. In fact, there's lots of properties that are known about trees, which is why they're very fashionable. So, for example, this is a nice property that every tree has, regardless if it's rooted or not. So I'm not focusing on non-rooted trees in this course, but this is just true about any one tree that you can throw at me. So let M be the number of edges. So remember, those are our links that connect the nodes. So this would be, for example, an edge right here. So remember, when I actually implement this, you can imagine this like it's an arrow that goes, so it's a link that goes from C to A as its child. And also I can imagine there's also a parent that points back this way. But I count these edges, these lines. So that's the number of edges, that's M, and N is the number of nodes. Here's the first thing I can tell you about a tree that's very fascinating, is that the number of edges is always going to be one less than the number of nodes. Now, the neatest part about this very cute property that exists is that it's very easy to convince you of this fact, and the proof is so simple I can write it in about 2 sentences. It's all entirely based on a very basic counting argument. So I thought I would give you the idea first of why this statement is true. So first, does everybody understand the statement that the number of edges is always equal to the number of nodes minus 1? Okay, so here we go. I'm going to give you the basic counting argument for this. You're going to find that a lot of these structures are very nice because they have nice what we call combinatorial properties for counting. So I'm going to show you how I can pair up the edges and nodes to show you this property is true. So watch this. So I'm going to imagine I take each one of these off. So imagine I could take one of these nodes here and the edge that connects it. And I'm going to try pairing them together. So you can imagine it like almost like it's a lollipop or a sucker, for example. So for example, I'm going to pair B with the edge that follows to get to its parent. So imagine it's just like I grab one of these and there's my sucker. So what I want to do is I'm going to do this for every one of the nodes. And remember, the strategy here is I would like to count them. I want to count the number of nodes there are and count the number of edges there are. So I'm going to pair them up like this. So watch this. So I'm going to pair A, I'm going to pair F with its parent, this edge that allows it to go to its parent. But there's one node that cannot be paired. Which one? Which one can't be paired? C, but what's C? It's the root. Yes, exactly. So notice that every one of these edges gets paired with a node except for the root. But what does that mean? There has to be one. There is always going to be one edge that isn't going to get paired with a node, right? It's always going to be the root in this argument. And that's actually where this comes from. So let me just write out the proof for you, and I'm hoping I will convince you that it's a very simple idea. So here's a proof that you can check over. It's a very basic counting argument. So pair every node with the edge connecting it with its parent. One node will not be paired, right? The root. Will not be paired. Will not be paired. It's a little squeaky marker. Will not be paired the root, right? We observed that the root is the one that doesn't get paired in this approach that we're using here. Well, that means that there's equal numbers of edges and nodes, except for that there's always one more node than there are edges, right? But that also means the following. Therefore, there is one less edge than nodes. And that's it. That's the proof. That's as simple as it is. So this is an example of something you would call a combinatorial argument. You'll see more about those in CS210, for example. It's very cute. Isn't that cute? That's a very cute argument. Notice I didn't have to pull out anything fancy-pantsy. This is very natural when you think of what we call discrete mathematics. A lot of structures like this have properties like this. So that's a great thing. That's a great thing, right? So I thought we would take to task the first thing we can try to do on a tree. So know how we talked about the height of a tree, which remember, the height of a tree is the maximum depth of a node. And the maximum depth, so the depth of a node, first, actually, before we get too far ahead, what is the depth of a node? So can somebody tell me what that means? What is the depth or level of a node? So what is that? Can somebody remind me? It's the number of ancestors a node has. Exactly. Exactly. So for example, in this tree right here, notice that if I find the maximum depth, that is the height. So notice that here, for example, if I pick off any of the B or E, notice that the maximum number of ancestors I can have is 2, right? 1, 2. So the height of this tree is 2. So we're gonna think about how we can actually calculate the height of a tree without any knowledge about what's going on inside it. So we're gonna start off by just trying to figure out, okay, so given this kind of representation we have, can we compute the height of the tree? So let's get on this. Now the first thing I really want you to notice about a tree, and this comes back to the very last thing I told you last time. Do you know how I told you about this definition we called the subtree? We called something called a subtree, right? And that is, if I give you the subtree of a given node, then that is that node and all of its descendants. So if I have that, think about this like this. So if I give you a subtree, you know how I talked about how that node operates like the root of that subtree, right? So this is going to be something that you're going to notice very quickly, is that trees are very natural to describe recursively. And hopefully you'll be convinced by this fact by even how we represent them, right? Where each one of them is a node, and each node has children, right? Well, I can always imagine I'm at one given node, and I can ask the question of the same kind that we talked about just a moment ago. What's the height of that subtree? And naturally, if I ask this on the root of the whole tree, like of the rooted tree, I can know what the height of the tree actually is. So let's talk about computing the height of a tree. I think that's a very good place for us to start. So let's try this out. So we're going to try computing the height of a tree. So just a reminder. The height of a tree is the maximum depth of any node in that tree, right? So I'm going to draw out a tree, and what we're going to do is we're going to come up with some way of calculating the height of the tree based on some of the things I was sort of alluding to. Now, there's sort of one detail that I mentioned, but I didn't really emphasize it much further. Remember that I only have access at the start of this process. I start access at the root, right? And you know how we talked about, oh, it's kind of like a generalization of a linked list, right? Just like you would start off at the head of a linked list at the beginning of a traversal. Well, the same thing applies with the tree. I start at the root of this tree, and I'm going to work my way through the tree. I need to explore it somehow to figure out what the height is. I don't have direct access to all of one of these nodes. Otherwise, if I did have direct access to each one of the nodes, what could I do? Does anyone have any ideas? So I'm just going to keep drawing out this one tree while you guys think about that. So suppose that I had all of the nodes directly accessible to me. Does anybody have any ideas of what I could do? And it comes, I'm giving you a bit of a hint. Well, like look at the definition of the height. And you remember how I talked about how each one of our nodes actually has access to its parent. And keep in mind, I'm not looking for anything more concrete than just an idea. I just want you to think a little bit about this, because there's at least a few different ways I can do this. I'm going to show you a very natural way of doing it, but I think it's important that we think about this a little bit. So remember, we have the root. So just for the sake of simplicity, I'm just going to call that R for the sake of our discussion. But suppose that I had access to every one of the nodes. So suppose that, say, for example, all of these nodes somehow were dumped into a collection or, say, an array. And I wanted to go through each one of those nodes. What can I do with each one of the nodes to figure out the height? What can I do? So like just imagine I took this and I dumped all of these into one array and I were to try to scan through them. Well, you can think about it like, say, if we're trying to compute the largest number, right? But what can I do to figure out the height of each one of those nodes? So actually not the height, the depth, right? Yeah, the distance from the root. Exactly. That's exactly it. So think about it. If I had access to any one of, all of them, what I do, remember, I have access to each one's parent, so I could just keep track of how many of them I go through. So I just would scan through my array, for example, from left to right, and I could just simply look at each one. I can make like a variable like cur, just like you would with a linked list, and I could just follow how many ancestors I have until I hit the root. And then I keep that count and I compare it against whatever my biggest number I have so far, and I could just simply do something like that, which is not much different than computing the largest number in an array. It's just the difference is we just have a little bit of work to figure out what the number would be. And the number in this case would be the depth. Now, I'm going to show you a way that's a little bit more slick than just this. And it's entirely based on the structure of the tree. So we're gonna try to figure this out by me just probing you with a bunch of questions about this tree. So what I was thinking, so I'm gonna ask you a bunch of questions. We'll figure out what's going on with this thing. So if I look at this node I've just circled in green, oh, this smells like apples. Don't do this with normal whiteboard markers. I'm not kidding, this smells like apples, specifically green apples. You could tell people after class, like, oh, my prof was huffing markers in class. They smelled like apples. So at least that might give you an indication of what we're doing today. But listen, I'm just joking around. So what's the height of this node? So if I looked at the subtree of this, so if I looked at only this, what would be the height of this one node? Well, I'm not looking for the height. Remember, I'm only looking at what I have in green. So imagine this is the subtree of this node. So if I look only at this node, that one in green, and I ask its subtree, what's the height? Well, does it have any ancestors if I only look at what's in green? It's 0. There are no ancestors. So I like the ideas here. So I could do the same thing with any one of these leaf nodes. If I look at the subtree at that one node, remember that is the node itself and all of its descendants. If I ask what the height of that tree is, the answer is 0 for all of them. So all of these ones I just put in green, if I were to make R that node, the answer would be 0. I'm not yet considering the entire tree yet. So we're working our way up to the root. So now, if I were to ask you, if I consider the subtree rooted at this node right here, what's the height of this node? Yeah, it's 1. Notice that, and this is the thing. This tree that I've just circled right here, that's rooted at this node, the height is 1, right? I was about to write that in green. Let's write that in 1. So this is going to be a 1 for its height. Also, I missed a leaf node right here. Right there, there's also that 0 right here. Okay, we can do the same thing right here, right? So notice that if I look at this node, and I imagine that as the root of the tree, so it's the subtree rooted at this node. The height is also 1 here. How about this one? This one right here where I'm rooting it at this node. What's the height of that tree? Yeah, it's 2. Does anybody see anything interesting that's happening here? Is there anything strange that kind of sticks out to you like a sore thumb? So yeah, the height with this one would be 2. There's something very interesting happening and I want you to really think about this carefully. So notice that when I think about the 2 here, notice that I have this subtree and this subtree, right? But those are rooted at the children of this node. Well, notice when I ask this question here, it's just actually like the actual one when I asked you this question. Does everybody see that? It's actually kind of interesting, right? So notice that before, when I asked you about these leaf nodes, you told me that the height was 0, right? Well, to figure out that the height was 1 for this, notice that this is just going to be an ancestor of the deepest node of its children, right? So notice that it's just simply whatever the bigger of these numbers seems to be, and I add 1 to it. Because I go up 1 ancestor. I work my way up the tree by 1 ancestor, right? Does everybody see that? Isn't that a little subtle? But it sort of sticks out at the same time. I know, that sounds wild, I know. You could say, Dan, you've been huffing too many of this green marker here. So look at this, look at this. So notice that if I asked you the same exact question about the entire tree, and now remember, I want you to just imagine the subtree of all of this, but only use the information I've just written out right here. The 1, 0, and a 2. What would be the height of the tree? Rooted at R. 3, right? And that's the height of this tree, right? So notice here that actually, when I'm doing this, I can just figure out what the height of each one of the subtrees is by just simply trying to figure out which one is the deepest or the tallest. It represents the tallest of all of the subtrees that form subtrees of my children. So if I look at each one of my children, the subtree that I have from that child, I want to know the tallest of those. And I just take whatever that is, and since I'm going up 1 ancestor, I add 1 to it. So let me write out a recurrence relation that represents this. So that's actually the key idea behind how I can compute the height. So notice that I don't have to go through every one of the nodes and compute the height manually and figure out which one's the largest. I can rewrite this in a somewhat different way based on the structure of the tree itself. So you're going to see that this is a very natural thing that what you can do with a tree. So you know that the height is 0 if R is a leaf, right? If R is a leaf node, then the height is 0. But otherwise, I have to figure out the maximum height of each one of the subtrees of my children. So just to be a little bit fancy-pantsy here, this is going to compute the maximum value across each one of my children, its height, and I'm going to add 1 to that for the ancestor. And I do this if R is internal. So remember, an internal node has at least 1 child. So this is another way of just saying what I just was saying verbally over here. Now, you might say, okay, Dan, so show me the algorithm now. So show me the algorithm. So this is a mayonnaise and mustard way of me writing out the height. Let's write out the pseudocode for how we can compute the height. How does that sound, everybody? That sound exciting? Give me 2 thumbs up. So we figured out how we can compute the height recursively as opposed to having to do all of that work where we have to collect up all the nodes somehow. And I haven't showed you really a nice way of doing that quite yet. So let's have some fun with this. So you're going to see that this algorithm is actually fairly concise. And it's entirely based on the fact that we can describe trees recursively based on the definition of a subtree. Because, of course, the subtree of the root node is the entire tree, just as if I were to consider the entire tree, right? So let's write out this algorithm. So we're going to have our algorithm, call it height, with a given supposed root. And I must stress that the way we're going to use this R for the root is going to be the root of some subtree. So the initial call of this would be actually on your root attribute for the tree. So when you represent the tree, and you call this on the root initially. So the input is going to be root R of a tree. And the output is going to be height of a tree. Technically speaking, it is the height of the tree rooted at R. So, just like I told you, whenever we have a leaf node, if R is a leaf, then I can just simply return 0. Now remember, if I have a leaf, I can tell you right away if it's a leaf it has no children, right? So that's one simple way you can recast this. Normally, what you would do is you come up with a function called ask it if it's a leaf or not, and it's a Boolean function like this. And the one way you can actually write it up is you would just ask, oh, is children null or not? Or if you have some internal variable that stores how many children you have inside the node, you can also do that as well. But typically the former is much easier. Otherwise, I'm going to have a variable I'm going to call the max height. And I'm just going to give it some initial value just to make sure I can always beat it, because the smallest height any one tree can have is 0 in our definition, because I presumed I already have a node, right? So I'm going to write this, you know how I told you I could go through each one of the elements in my collection, whether it be an array, whether it be a list or a vector. I'm going to use what we call a for each loop to describe this. So there's different programming constructs like this that are capable of getting this structure like this. So often it's written like for, and then you have each one of the elements that you have in your collection. So it's like for something that will be a placeholder for the collection object, then in this other object or collection. But the point is I'm going to go through each one of the children. That's all you need to know about this. for each child C of R, we're going to do the following. I compute the height. So I'm going to do a recursive call on the child C. And then all I'm going to do is ask if that is, in fact, bigger than the current maximum height I have. So if h is, in fact, strictly bigger than max height, remember that if this is true, that means I found a taller subtree among my children. So remember, the game is I'm trying to figure out which of my subtrees among my children is the tallest. Then we just update max height. So I'm going to update max height to be h. And lastly, I just simply return whatever that max height is, and I add 1 to it, right? Because you want to imagine this like I'm going to consider all my children, then I'm going to look at me, the node. It's me, the node. So you see that really I'm actually using a couple of different ideas here. So 1, I'm using the fact I can go through all my children. 2, I'm using the idea that I could just keep track of which one is the tallest of my children when I look at their subtrees. So I want to know which one has the highest depth, akin to the first idea I told you about. But notice now that because of the recursive nature of the tree, I could describe it in terms of my children. So I could take each one of my nodes, I can imagine I can look at each one of my children and I can ask the question. Is that clear, everybody? So notice that if I had no children, notice the reason why I picked this to be -1 like this is I would end up with max height plus 1, which would be -1 plus 1, which is just 0. But I write this more explicitly like this just for the sake of simplicity, just in case if, say, your collection is in fact null versus not null, which I want to just keep things simple. So does this algorithm make sense to everybody before we analyze it? Because we haven't really done, we've seen recursive algorithms, we've seen some ideas for how to analyze them, but we haven't done anything on a tree quite yet. Okay, give me 2 thumbs up if you find this kind of fascinating. So we took a bunch of different ideas that actually we've had before. For example, computing the largest number in a collection, to thinking about it recursively like this by exploring a tree. So let's get on this. So actually, before that, let's get back over here. Get back here. Go over there. Go over there. So let's analyze this in the way that we're used to doing. So first, we start off by ignoring the recursion. So we ignore the recursive calls. Notice that the number of recursive calls here actually is remember, the recursive call is right here. So notice that I'm going to start off by ignoring that. So let's figure out what's going on here. So remember the base, so actually first, so what is the base case here versus the recursive case? We should probably figure that out. So what's the base case? What's the recursive case? So yeah, this if statement, that's the base case, exactly. Because when we hit a leaf node, we know the answer. We know the height is 0. We know that. And then this is the recursive case. Very good, very good, very good. So let's analyze it, keeping this in mind. So remember, in the base case, notice that I'm going to do some constant number of operations because checking if it's a leaf takes constant time. And of course, returning 0 takes constant time. So I'm going to have some constant number of operations there. Now, otherwise, we have the recursive case that happens. Now, technically speaking, it will execute all of this. But for the sake of simplicity, I'm just going to, let's see. I'm just thinking here if I want to do it that way. Let's do it this way. Let me do this way. So let's do this. So for each one of the children, notice that inside of here, if I ignore the recursion, because remember, this is a loop, right? So I'm going to have some C3 many operations that are going to happen in here. And of course, everywhere else outside of this. So all the stuff that's happening outside of the for loop, this is some other constant number of operations, right? So you can see for each one of our calls, what would be the time complexity for computing just one call of this, ignoring all that recursion. So notice it's C1 here to just check this, and even if you return, otherwise you have some other constant, many operations that happen outside of here, and then you have something else going on right there. We have C2 with something else, right? There's something I have not counted for quite yet. What am I missing here? There's something I'm missing right somewhere about in the middle over there. Yeah, the loop, right? I did not account for the for loop. Exactly. I have not done that quite yet. So notice that this depends on the number of children, right? The number of children of R. So this for loop combined with C3, well, this is going to be, let me just write this out over here. My apologies. Normally I do this with multiple colors. So this would be C3 times, and I'm just going to write this for the sake of brevity. I'm going to write it as a function. Call it numchild of R. So numchild of R will just be the number of children of the node R. So if you put this all together, you end up with something that looks a little bit easier to actually write out. So let's proceed from there. So let's combine all of this together. We'll end up with a complexity function. And then we're going to see what we can do with the information we have to study the tree. So we're almost there, believe it or not. We're almost there. We're just we haven't yet dealt with the recursive stuff quite yet. But you're going to see that trees are very natural for capturing this kind of stuff. I would argue even simpler than some of the things we've seen earlier in this course. Okay. So let's talk about the time complexity now. So I have a more detailed explanation of this. So in the base case, so what I've highlighted as the base case, there's C1 many operations that happen. In the recursive case, regardless of what happens, you're going to have C2 plus whatever all of this stuff is going to happen in the recursive case. You can also throw C1 in there off to the side, but it'll end up just being some constant amount of operations that are going to happen anyways. So it doesn't make much of a difference to throw it in or not. So the first thing I want you to notice is what happens with the recursive calls. So I'm going to combine all of this into... Actually, before I write my observation, let's figure out what's happening with one call. So let's put it all together. I'll have to get a little ahead of myself. So in the base case, we have C1 operations that happen. So in the part that we indicated is the recursive case, we have C2, yes, C2, plus C3 times the number of children, which we called numchild of R. So this is the base case. This is what happens, what we indicated as the recursive case. So we're just going to put all this together and count up all the operations. You're going to see I'm not going to be using techniques like iterative substitution or anything like that here. The beautiful part about a tree, like I told you, it's very natural to describe things recursively over trees. And you're going to see that in a moment. So I'm just going to give you a little doodle of a tree here, just so we can get an intuition for this. So just imagine I give you a tree that looks kind of like this little cute one. Look at this tiny cute thing. If I give you each one of these nodes here, so when I initially call this at the root of this tree, notice that I have the initial call that happens there, and then what it does is it scans through all of the children, right? It goes through this child, this child, this child. It calls height on each child, right? So it does one call here, and it's going to do 3 calls, but recursively speaking, it'll call this one, then it'll call that one, then this will examine all of its children. And it'll say, okay, I found a call there, but it's going to go through each one of the children like this. So what's happening? How many recursive calls actually happen? Well, actually, not just recursive calls, but how many even function calls happen? So in the entire execution of this algorithm, how many calls actually happen then? Yeah, it's the number of nodes. Yeah, very good, very good. Yeah, very good observation there. I like that. So observe that the number of calls, so this is just me bringing in all that recursion now. Observe the number of calls, so this is overall the entire execution of the algorithm. The number of calls is 1 per node, right? I do this for each one of the nodes. So notice that in our base case, we do some number of operations. Then we have all the stuff that happens with the internal nodes, right? So I'm going to lump them in these two separate buckets. The ones that happen for the base case code. Then there's the stuff that happens for the recursive case. Again, like I said, if you wanted to, you can also throw in C1 with each one of these calls that happens at the internal nodes, but it makes no difference. It's just going to be some constant that's just sitting off to the side. So watch this. Thus, the total number of operations is the following. It's the sum over all of these cases that happen for our base case code. So this gets summed over all of the leaves or leaf nodes in the tree, right? Because the base case happens when we hit a leaf, right? A leaf node. So this accounts for this right here, plus all of the stuff that happens otherwise in the recursive case. So the recursive case happens, and remember, like I said, technically speaking, you can also throw in C1 in there if you wanted to. I'm just for the sake of brevity because it won't make any difference because C2 here is still some constant number of operations. It may as well encapsulate C1 too. Remember, it's just some constant number of operations. So remember, that's what C2 is. It's just some constant number of operations. That can also account for the if statement up there. So this C2, it pretty much can have this in there too. So C2 plus C3, and remember we said that this is times the number of children of a given node. We'll call it, instead of R, just for the sake of simplicity, I'll call it U. And I'm going to do this over all of the internal nodes. So remember, there's only two kinds of nodes in a tree, the internal nodes and the external or leaf nodes. So this is going to be summed over all of the internal nodes. So for each one of the internal nodes, you know it happens because it's not a leaf, right? So this represents the operations that happen in the recursive case. This is the operations that happen in the base case. Is that clear, everybody? Are we okay with this so far? We have to do a bit more with this, right? We're not quite done yet. So let's proceed now. So I know I have some number of leaves here. So notice that this is just a sum over the number of leaves, right? So I'm going to just explicitly write that out. And notice I have some constant here. Well, I'm just summing this as many internal nodes there are in the tree, right? So I'm just going to write these two out. So I have C1 times the number of leaves in the tree. So I'm just going to write that as number of leaves like this, just for the sake of brevity. So I don't write this out as like a function or something. I'm just going to keep it simple. Then I'm going to distribute this sum over two parts. So I'm going to have C2 times the number of internal nodes, because that's how many times I add up C2. Then I have to deal with this. Notice that the C3, which doesn't depend on U, but does numchild U depend on U? Yes or no? Yes, it does. So we're going to keep that inside of the summation. So remember, I could just take this C3, just throw it out there in front, and I'm just going to write numchild of U. And this is over all of the internal nodes. So I'm going to sum over still all the internal nodes. I've got this set up. Now here's the fun part. Well, let's think about it. Let's think about this very carefully. Let's see. Remember, this is the recursive case. Right? That's the recursive case. So when I do a recursive call, I do a recursive call. I do it over all the children, right? So I got this, right? Do you remember I told you something about like how we can count the edges versus the nodes? So you notice that when I make a recursive call on each of my children, right? Say, for example, I'm right here at the root, and I make each one of these calls here. Notice that each one of these calls is each of my children, which I can pair with each edge. Does everybody see that? This should remind you of something we just talked about, how we're counting up the edges, right? So the same thing applies here at this node, this node, this node, this node. So notice that when I'm counting these, notice that when I do this, actually I don't do it actually at these nodes. I don't have to do it at those ones, because remember, I'm only counting about the internal nodes, right? So when I make recursive calls at internal nodes, let me generalize this entirely together. So when I start at the root, I make 3 calls on this tree, for example. Each one I can pair with an edge. At this internal node, I make a recursive call to my children, which is at a leaf node. But the thing is, I still make this call regardless. I do it at this node because it's an internal node. I do it at this node as well. I call on all of these nodes regardless in the recursive case, right? But watch this. How many calls are actually happening in that case if I look through my loop? Well, it's the number of children at each one of the nodes, right? But what's that mean when I sum over all of them then? All of those children? Well, the sum of the number of children for all the internal nodes, because remember, I want to know this right here, right? For all the number of, so for all the internal nodes is the number of edges. It's just the number of edges. Does everybody see that? If you don't see it, let me know. I will go through it one more time. Is the number of edges. So just think back to our suckers. Each one of those recursive calls, it's like I'm generating a sucker. It's just the number of edges m. And we know from the tree property we just talked about that m is equal to n minus 1. So we have the following. So let me simplify this now one step further, and then we'll be done our analysis. So let me finish that up over here. Okay, let's do this. We got our last step in this thing. So now we're going to just plug in wherever I have... Well, get back here. Get back here. Get back here. Get back here. We have to finish this up. The camera's walking away without me. So let's put this all together. Oh yeah, I have so there. So let's just wrap up the sentence then. So... this means that this all is equal to C1 times the number of leaves plus C2 times the number of internal nodes. Whoops, internal plus C3 times n minus 1, right? Because if we sum over all the internal nodes to get the sum, how many total children there are, it's actually equal to the number of edges. So that's what we just concluded. But here's the neat part. How many leaves can there be at most? Just think about those two main things. Like we talked about M and we talked about N. What can we say about the number of leaves? Surely there can't be more leaves than there are actually of nodes, right? So I'm just going to be a little generous with my analysis. I'm just going to say, hey, look, the number of leaves most certainly cannot exceed the number of nodes in the entire tree. You can say the exact same thing about the number of internal nodes. So you can say that this is at most, well, I can replace each one of these with n here because those are all going to be smaller or equal to it. So I'm going to just rewrite this as C1 plus C2 plus C3 times n. But what's this in big O? What is the big O? What's going right here? It's n, exactly. That's exactly it. So we've concluded that the worst case time complexity is big O of n. In fact, you'll notice that the behavior of this algorithm just seems, it's quite oblivious to what you do exactly with the tree. It's just go through the tree regardless. So that's what the time complexity is. It is big O of n. So notice it's pretty slick, right? So I don't have to do anything else. I just explore the tree. So this is a feature of what we call tree traversals. So notice that when I did this, I went through the tree and I actually examined the heights of nodes. But to do this, I explored all the way down to the bottom of the tree to get to those leaf nodes, those sweet, sweet leaf nodes. And obviously, don't go out into go out there and start eating the leaves. I tried it once. Don't do it. Don't do it. They aren't that sweet and delicious, okay? So at least I haven't. I could be very surprised. I kid, of course. So this is actually an example of an algorithm that uses a tree traversal. Just like you know how we talked about traversing, say, a linked list, you can traverse trees too, and it often builds the backbone of how you can solve problems on trees. So we're going to talk about tree traversals next, and depending how far along we'll see if we have enough time for an example. If not, I'll get you to take a look at it. But this is one prime example of a tree traversal. So the whole idea is that I examine the tree by exploring its children to figure out information before I ultimately know the answer of what the height of my subtree is. So this is actually an example of one of these tree traversal algorithms. So you can think of this like a framework to design algorithms to solve problems on trees. So what's a tree traversal? It is simply, so a tree traversal visits the nodes of a tree in a systematic manner. I know it sounds like such a cop-out definition. A systematic manner. So I'm going to define what these are in a moment. In a systematic manner. But let me give you a couple of ways we can traverse through a tree. There's more kinds of tree traversals. But remember, we're talking about a very general structure here. So I'm going to introduce you to a couple of different ways we can traverse a tree. So I'm going to start off with two, but you're going to see a couple more ways we can traverse through a tree as we specialize their structure. There's also another one we can also do on generalized trees like this, but I'm going to hold off on it until we get to our more what I'll call cardinal examples of data structures on trees. So let me define a couple of these and we'll play around with them. So the first one is what we call a pre-order traversal. So the name, the prefix pre should give away what we're going to try doing. And they're all going to be defined like this in a recursive manner. So a node is visited. So there's going to be this operation I'm just going to colloquially refer to as visiting a node, which can be where you do stuff at a given node. A node is visited before its descendants. Before its descendants. Before its descendants. That's one of them. I'm going to give you kind of like a quick sketch of what the pseudocode of this looks like. So actually, I'll hold off on the pseudocode for now. We'll write it on that board in a moment. I'll define also the other one that we're going to talk about, the what is called a post-order traversal. Based on the name alone, could somebody tell me what you think a post-order traversal does as opposed to a pre-order traversal? So a pre-order, post-order. What would a post-order one do then? This is the great thing about a lot of terminology that's used by computer scientists. It's pretty like, the words sort of just give everything away. It's after, exactly. It's after its descendants. Exactly. So it's a post-order traversal. So in a post-order traversal, a node is visited after its descendants. So remember, like I told you, the idea here is that we're going to have it where we're going to have these operations I'm going to refer to as a visit. So it's after its descendants. So you got to imagine this like, I'm going to explore the tree, but I have this vague operation I'm going to call a visit, which you can easily modify to do other stuff. But the point is, the order in which I apply this operation, this visit, is determined by the traversal. So you're going to see this in a moment here. So I'm going to write out the pseudocode for both of these. You're going to, like I said, you're going to see this like a framework for designing algorithms that you can come up with for trees. So you can look at this like the backbone for designing different algorithms that you can use to solve problems on trees. So it itself is an algorithm. It's just the thing is, I want you to think about it more like a pattern or a strategy for how you can solve problems on a tree. So if we have certain operations we'd like to do with the tree, you're going to see that a lot of them are going to be built around us just taking this thing and applying one of these traversals, or specializing it further from there. So if ever I need to explore the entire tree, a tree traversal is usually your best friend. Sometimes we can use much more specialized versions of these. Other times, not so much. So here's some pseudocode. You're going to find that this is going to be really short. It's going to be some of the shortest code I'm going to show you in this course. So I'm going to have an algorithm I'm going to call pre-order. Imagine I give you as input a node V. And I'm also going to have another algorithm. And that's not the entire algorithm, by the way. I'm just putting them side by side just to illustrate the point. Post order. And it's going to take in as input a node. So in the pre-order, I'm going to visit. So I'm going to have this visit operation I'll do. So remember, what would this be? This would be something I do at that node. So just look at it like a framework. So you could literally have a function you call visit if you wanted to, but you can easily see how you can adapt this to have like, oh, I have some variables. I'm going to do something at that given node, whether it be calculations or something along those lines. So hopefully I'm clear enough about that. So for each child C of V, so for each one of the children, all you do is you apply pre-order. So pre-order on each child. That's all it is. That's all it is. And then this one, because of what we just described, you go through for each child C of V. We go through all of our children first, so we're going to recursively apply post order to each one of my children. And then after this loop, after the loop, I'm going to then visit it. And that's it. See, these are pretty nice, right? But it'd probably be better we do an example so you can actually see what this actually does. So the first thing I want to ask you about is coming back to our example where we had height. So when we looked at the height, right? Remember the whole idea when we computed the height was we examined all of the heights of the subtrees rooted at our child or our children, right? And then what I did is I picked the largest among them. And then I returned that and I added 1 to it. Which of these 2 buckets would our height algorithm fit better into? So which of these 2 seems a little bit more to what I used to kind of build that algorithm? So for example, did I do stuff first and then I visit all my children to figure out, and did I figure out everything first and then I go and did stuff with my children? Or did I figure out the answer by examining all my children? Exactly. You'll find that my example I gave you with the height is a lot like a post-order traversal. That's actually what I adapted to design that algorithm for you. Now, it's a well-known algorithm, but I'm just being colloquial here. Is that it's a good example of me using a post-order traversal, but that algorithm is rather simple, so it's really kind of, I can understand why somebody would be looking at it like, okay, well, you go through all the children, but but remember, the work I do is I determine the answer after I examine all my children, right? Exactly. So it doesn't necessarily have to look exactly like this. It's just that this is a framework. So that's why I'm saying that it's literally an algorithm, but it's also a framework for adapting it to solve problems. I hope you see what I mean based on that example. I'll have another example in the notes. I'm just looking at the time here. I'll have another example in the notes showing you how you can compute. Say, for example, if I gave you a tree that represented a file system, how you could use it, use an idea of a post-order traversal to figure out the total amount of space that's being used by all the files. So you'll get to see another example. It should remind you a lot of the height example we did here today, but it's just that instead of figure out the maximum, we're just going to add things up. We're going to have a running total. So anyways, I thought we would do an example with the post-order traversal. So I'm going to draw out a tree, and we're going to walk through step by step through the different traversals here. So let's draw it with a tree here. So I have A, B, C, and D. E, F, C will have G as its child. G will have children I and J. And D's child will be H. So what we're going to do is I'm going to remind you that, remember, we're still using recursion, right? So there's going to be a call stack somewhere in this process, at least when we talk about this. So remember, I still have the call stack in play. So when I start this process up, keep in mind, like I said, a tree is it's recursive in the way you can define it. So what you can do is you can even start a post-order or pre-order traversal at any one of the nodes, technically speaking, if you had access to it. So for example, if you had direct access to node C here, you could run post-order from C and start there. But typically when you go through this traversal process where you want to examine the whole tree, since you only have access to the root, you start off at the root. So regardless of which traversal we're going to use, we're starting off at A. So I think we'll start off with the pre-order traversal, and then we'll do a post-order traversal. So let's start off with the pre-order. So you know it's going to first start off with A. So now, what I have to do, remember, I'm going to visit that node. So I'm going to put them in the order I visit them. So when I do this visit operation, that's the order I'm going to put these nodes in my listing here. So we're going to then need to visit each one of the children. So I have to go for each one of the children. So I'm going to have to call on B next. So I call on B. So remember, I've already visited A. Then I'm going to go to B. Because remember, that's the first child here. Now, technically speaking, it could be any one of the children that this would make this work. But since I am just keeping this simple for us to sweep from left to right, I'll just do it this way. When we actually have trees that are prescribed in ordering, like a very explicit ordering, you'll see that it actually does matter which one you do first. For example, if I were to designate this always the first one, then this the second one, then the third one, like in the way we're going to do this, some trees explicitly force an ordering like this, as we're going to see in the next lecture. So next, notice that I visit it. And then I examine my children, right? So I visited B, then I examine my children. Because remember, I'm still doing this recursive call, right? So when I do the initial call on B, so now I'm at B right now, I'm going to go through each of my children. So I call it on E. I visit E. I'm done with E because there is no children for this node, right? I just visit it and I'm done. That means I visit my next child. So I have F. F is a leaf. I'm just done with here after I visited it. Now next, I go to my next child here. I'm going to visit here. So F, I get C. Now, this is an internal node, so I'm going to call on my child here. I have 1. I'm going to visit that one next. So I have G next. Then I go through each of my children. Oh yeah, I got to make sure I update my call stack. I have G right there. And then I go through each of my children. So I go to I and then J. I. Oh no, I'm starting to run out of space in my stack. I have I and J. Well, before J goes on there, I'm going to finish up I. So I have I, and then I would call this on J. So this entire subtree rooted at this child is done. And we're going to have our last 2 here. So D is going to get pushed on here next. I visit D. I visit D. And then I have a child, so I'm going to visit that child, which is H. And now H would be at the very top here. I finish at H. I am done at D because I considered all my children. And now I'm done. Wait, I should have got rid of B much earlier on. My apologies. B should be gone long ago. For some reason, I didn't see it there. G as well. G is supposed to be gone here too. My apologies. Then we have C is also gone, because that should have been gone earlier as well. My apologies. And of course, we have A being finished. So the whole idea with this process is I examine all my children, but I visit them first, and then I look at my children. But remember, I call this on each of my children. So remember, it is recursive, so you have to keep track of the stack, as I wasn't at the end there. But the top was okay. Just the middle, I sort of forgot a couple in there. But we get the right idea here. My apologies, everybody. I thought I got them there. But the whole idea is you visit. Remember, if you just get the main idea, you visit yourself before your children. But you have to visit them in the order you examine the children. So keep in mind, whenever I look at any one of these, it better be that I appear before anywhere my children appear in this listing later on. So anyways, with the post order, I know we're pretty much out of time here. I'm just going to make a note of what the post order for this is, and then we'll stop here. So the post order here, remember the whole idea is that you visit all your children first. So I want you to walk yourself through this tree. So just follow that to the T. And you're just going to visit your children first with the recursive calls. Then you'll visit yourself at the end. Remember, this is just like the example we did with the height. So the order in which that algorithm visited the children is the same one that this algorithm will. So A, it goes A, B. Sorry, I'm writing it. My apologies. I'm going to the pre-order. I want post order. My apologies. I've been huffing that marker a little too much. I'm kidding, of course. My apologies. E, F, B, I, J. So I want you to try on your own to try walking through this. If you're not sure, go through how you might do this with that height algorithm. So I have E, H, B, I, J, G, C, H, D, and then A. And if you look at this ordering, this shouldn't be very surprising because you visit yourself after all your children. So when I start up here, I go through all, I don't visit myself until all my children have been visited already. So if I'm at this node, for example, I know that these two are going to appear before myself, but notice it's dictated by the order in which I call all my children. So in this case, notice that I don't see B in my listing until all my descendants appear in the listing. That's one way you can quickly check if you've done it correctly. So notice here, I visit this child, but notice that I don't actually visit it, right? I need to visit all my children, just like here. So I visit these, then I can visit myself, then I go to my next, go to its children, then it goes to its children, I go to G, then C, then I go to its child, the last child here, same idea here, I visit here, then here, then here. So remember, just before is pre-order, post-order is after. Okay, so my apologies, everybody, for that oopsie on the call stack. That's very rare for me to do. So when we come back next time, we're going to start talking about so-called binary search trees, which are going to be relevant for the final assignment. So when you get a chance, take a look at the example I have in the notes for another case of the post-order traversal. So the one caveat that you have with this post-order traversal is that you can actually visit all of your descendants before yourself. It's very often used when, for example, you want to compute like the largest value among your children, like we've seen with our height example. But also it's very useful, for example, if you need to take structural parts of the tree and delete those without affecting other parts of the tree. So for example, if I wanted to delete this node, but not like dissect some other part of the tree, post-order traversals, if I'm looking for a particular node, I can always snip it off, almost like I'm snipping off a branch. So that being said, I would say thank you very much and have yourself a beautiful day. I'll see you later.